engineers and physicists never really worry too much about these details because the functions that they encounter are ones that can all be differentiated. You go find a primitive. That's how you do all these. I will evaluate the integral by finding a primitive. And they're used to saying that and always being able to find it. As mathematicians, we say, well, that's nice when you can do it, but the integral still may exist even though you can't find a primitive. Right? They're out there. You just can't find a primitive. Okay, sorry. All right, so let's turn the on switch to on and really, in order to successfully define, as I talked so much, Michael, Henry, dry and Cauchy integral, and the Riemann integral depend critically on the fact given by Heinz, which says if f is continuous on the closed interval AB, then f is uniformly continuous on AB. If any of this notation is unfamiliar to you, C with the closed interval means it's a continuous function on AB. Sometimes people will write this, C0. That refers to the order of derivative that is continuous. So a C0 function, what they're telling you is the function is continuous, but its derivative may not be. If they would say C1 on AB, it would mean the function is continuous and it has a derivative that's continuous. But the second derivative may not be continuous, right? So if I have an R here, it means up to and including the rth derivative are continuous. Okay. So Heinz theorem is critical. And Heinz theorem was not available until the mid-1880s. And Cauchy didn't know about it. But so Cauchy's definition was defective in a philosophical way. He was right, his intuition was correct. He made an argument that a continuous function is Cauchy integral. He didn't have this theorem to really nail it down.
What's the little zero? What does that mean?
C0. CR of whatever you put here, is very often it's an open or closed interval, AB, means if a function is in that class of functions, it has up to and including its rth derivative on the closed interval AB, they're continuous. So Heinz theorem depends on that. And of course, Heinz theorem depends on the Heine-Borel theorem. Which says that the compact sets of reals are precisely closed and bounded sets. That is a very major theorem in analysis. Did you do that one in analysis? You must have. Even did it? Yeah.
Did it at the very end? Like Marx told us that compact sets were closed down.
Really? What? Oh. Pardon?
Yeah, I don't remember the definition.
Oh, really? Okay, well let me give you all that. Now's the time to look at this. And the Heine-Borel theorem depends on Cantor's intersection theorem. And that's wordy to explain how when we prove that one, I'll give you a statement of it. Basically, if you have a collection of nested closed intervals, minus 1 bn minus 1, right? So the next one is always contained in the last one. And the limit, as n goes to infinity, of the length of the nth one being 0 means that if you intersect them all up, there's a unique point common to them all. That's sometimes called the nested interval theorem. It works in metric spaces too, so it's sometimes called Cantor's intersection theorem. And Cantor's intersection theorem depends on the Bolzano-Weierstrass theorem, which says that a bounded infinite set of real numbers has a limit. So there's a pedigree here that is non-obvious, but in order to really successfully establish it, we have to fight through these things. So I thought we'd spend this week proving some of this stuff. It's good fun from analysis. You probably have seen a lot of this stuff. And if you haven't seen Hyatt-Burrell, we can prove it, and you should know how to prove that. But let me start with something really simple. We'll get our feet wet here and see where we're going. So the plan is to start proving the simple stuff and work our way up. Hyness theorem will be the high point. And then Hyness theorem, by the way, on page 33, under the proof of theorem 2.2.1, item 1, that's Hyness theorem. Which he just says, oh, by the way, this is true. So let's prove it. Why not? We got time. The triangle inequality. Who can prove that for us? Well, lacking that, who can state that for us? It says that if I have real numbers, x plus y, and I add them together, that's never greater than their absolute values. And what's an elegant way to prove this? Well, here's another. X plus y absolute squared is the same as just x plus y squared, right? Because it's positive. And that's x squared plus 2xy plus y squared. And then that's the same as x squared plus 2xy plus absolute y squared, right? Every time you have a square, you can substitute its absolute value. Note that 2xy is never greater than that, right? Do you agree with that? So we can substitute that in here and discover that this is true. Does anyone recognize how that could be pressed?
Oh, yeah, see right hand side.
Okay, now take the positive square root. Okay? By the way, why is it that positive square roots would preserve order?